Hello, statistics scholars. This is our first lecture for Chapter 2, Descriptive Statistics. This chapter covers the basics on how to describe data sets graphically and numerically. This chapter will show you how to organize and summarize data in a useful way. Here are the learning objectives for Chapter 2. This is what we are going to go over, and this is what you will need to know for the proctored quiz. Think of these learning objectives as your roadmap through the chapter and your study guide for the quiz. So take a minute, hit the pause button, and read through these. All right, so in this lecture, we will focus on describing data using tables and graphs. So let's begin. So how do we present raw data in a useful way? As researchers, we use frequency tables and graphs. First, let's talk about frequency tables. Frequency tables are used to organize data into what we call a frequency distribution. A frequency distribution lists each category of data and the number of occurrences or frequency for each category of data. They list all possible values for a variable along with the number of observations for each value. A frequency table lists each category of data and the number of occurrences for each category of data. In other words, a frequency table shows how many observations are in each category. The frequency represents the count of each category. We are also interested in knowing the relative frequency of the categories. The relative frequency is the proportion of observations within a category. We can find the relative frequency or proportion of each category by taking the frequency in each category and dividing it by the total number of observations in the data set. To get the percent or the percentage, we just multiply our proportion by 100. So here is an example of how relative frequencies are calculated. Now what happens if you have a larger data set or a large number of categories? We have to create what are called grouped frequency tables. Your textbook shows you how to construct a grouped frequency table. However, for this class, you will not need to. I do want you to understand the advantages and disadvantages for using grouped frequency tables. The main advantage is that you can quickly organize and summarize large sets of data using these tables. The main disadvantage is that individual data are lost when categories are grouped. The individual scores can't be retrieved. So here's an example of a grouped frequency table from your textbook. What you'll notice, as you can see, we have no way of knowing what the individual scores are. All we have is the frequency of scores in each class interval. Once raw data are organized in a table, we can create graphs. Creating graphs allows us to see the data and get a sense of what the data are saying about the individuals in the study. Usually, pictures of data result in much more powerful messages than tables, and people are more likely to remember information from a graph than they are from a table. So let's start with graphs for quantitative data. Dot plots, stem plots, frequency polygons, and histograms are a way of summarizing or describing quantitative variables. Your textbook talks about dot plots and stem plots, but I'm not going to go over them. Just know that these two graphs are best used for smaller data sets, usually less than 50 observations, and each individual score is displayed in these graphs. We'll start with frequency polygons, which are graphs that summarize and describe discrete or continuous data from grouped frequency tables. They are a special type of line graph. These graphs are especially useful when you want to compare distributions like this one that looks at students' final test grades versus their final grade in the class. This graph is very informative and relatively easy to interpret. In this example, we can see that there is very little difference between final test grades and the final grades in the class. Histograms are a very popular graphing tool that is used to summarize and describe discrete or continuous data from grouped frequency tables. They are especially useful for describing large data sets. Histograms display the data by using vertical bars of various heights to represent the frequencies. A histogram is constructed by drawing bars for each class of data. The height of each bar is the frequency or relative frequency of the class. The width of each bar is the same and the bars touch each other. In a histogram, frequency is measured by the area of the bar. This is going to be very important when we talk about normal distributions and z-scores later on. So which graph do we use? We've looked at different ways to display quantitative data. Polygons and histograms and dot plots and stem plots in your book. Which graph should you use? The dot plot and stem plot are more useful for smaller data sets, 50 or less observations, because they retain each individual data value. With large data sets, histograms are most useful. Researchers have more flexibility in determining the class intervals. And polygons are used to compare two different distributions or data sets. Now let's look at graphs for qualitative data. First, let's review. What are qualitative data? Remember that qualitative data provide measures that categorize or classify an individual. When qualitative data are collected, we are interested in determining the number of individuals observed within each category. Bar charts and pie charts are a way of summarizing and describing qualitative, nominal, and ordinal variables. Bar graphs, perhaps the most common data display used by the media. A bar graph breaks qualitative data down by group, showing how many are in each group. A bar graph represents those groups by using bars of different lengths. A bar graph uses either the number of individuals in each category, the frequency, or the percentage, or the relative frequency or proportion of the total in each category. A bar graph is constructed by labeling each category of data on a horizontal axis and the frequency or relative frequency of the category on the vertical axis. Remember, the horizontal axis is your x-axis and the vertical axis is your y-axis. Bars of equal width are drawn for each category. The height of each bar represents the category's frequency or proportion or percent. The bars do not touch each other because the data are discrete. There is no overlap between the categories. So here is an example of a bar chart from your textbook. Now here are some tips for evaluating a bar graph or bar chart. Make sure that the bars all have the same width. Take a look at the scale of the bar graph, the y-axis, and determine if it is an appropriate representation of the information. Never assume the information being presented in the bar graph represents everything you need to know. Be prepared to dig deeper if you need to. Pie charts. Pie charts are easy to read and can quickly make a point. You most likely have seen them before. They are pretty simple. A pie chart takes qualitative data and breaks them down by group, showing the percentage or relative frequency of individuals that fall into each group. A pie chart is a circle divided into sections or slices. Each section represents a category of data. Because each individual in the group falls into one and only one category, the sum of all the sections in the pie should be 100% or pretty close to it, subject to a bit of rounding error, of course. Pie charts can be created only if all the categories of the variable are represented. Here's an example of a pie chart from your textbook. Here's some tips for evaluating a pie chart. Check to be sure the percentages add up to 100% or close to it. Beware of sections of pie or sections of the pie chart called other that are larger than many of the other sections. This indicates that the researcher did not, or probably did not, identify all of the categories. Look for a reported total number of individuals in each group. This is a critical piece of information needed to assess the accuracy of the pie chart. Notice the pie chart in the textbook doesn't give you that information. Pie charts should be used sparingly for two main reasons. First, they are best used to display statistical information when there are no more than 6 categories. Otherwise, the resulting chart will be too difficult to understand. Second, pie charts are not useful when the values of each category are similar because it is difficult to see the differences between section sizes. Both pie charts and bar graphs are simple to construct or to create. Which do we use and when? If your objective is to compare the relative size of each category to one another, use a pie chart. The emphasis is on comparing the categories to the whole. Bar graphs or bar charts are more useful when you want to highlight the actual data values. The emphasis is on just comparing the different categories. Bar graphs are more flexible and more precise than pie charts. Now that we've looked at different types of graphs, let's discuss how to interpret them. Whenever we go about describing a set of data, there are 3 main things we will always want to know: the shape of the distribution, the typical value or measures of central tendency, and how spread out the data are with measures of variability. Creating a graph is just the beginning. The purpose of the graph is to help us understand the data. After you create a graph, always ask yourself, what do I see? Graphs that display quantitative data describe the frequency distribution of the data. The distribution of a variable tells us what values the variable takes and how often it takes these values. Another way to put it, a distribution is how values of a variable are arranged by showing their observed frequency or occurrence. A distribution shows the pattern or shape of how data values are spread out. With any graph of data, we always look at the overall pattern. Are the data spread out or close together? Do a couple of the data values seem further away than the rest of the data values? The three main features that we use to describe the overall pattern of a distribution are shape, center, and spread. Let's look at shape first. Shape of the distribution. Modality of a distribution will tell us the score or scores that occur most often. Are there major peaks? Single peaks, which means the distribution of data is unimodal. Double peaks, which means the distribution is bimodal. Or multiple peaks, which means the distribution is multimodal. Oh, and by the way, no peaks means no mode. And there are times when a distribution will have no mode. Is the distribution or the shape symmetrical? If it is symmetrical or bell-shaped, then the right and left of the distribution are approximately mirror image of each other. Is the shape of the distribution skewed to the left or right? Are scores piled up on one side and tapered off in a tail on the other side? This could be a result of outliers that extend the tail of the distribution in one direction or the other. If the left side of the distribution extends further out, the distribution is skewed to the left or is what we call a negative skew. The distribution has a long left tail. When you look at the graph, you will notice that most of the data values and the peak are on the right. The tail of the distribution is pointed towards the left, where there might be low data values that could be outliers or extreme scores that do not really fit with the rest of the data. So examples of distributions that are left skewed or have a negative skew would be students' scores on an easy test, where most students received or earned high scores and a few got low scores. Retirement age, where most individuals retire at an older age, and there might be some younger folks who retire as well. Another example, human lifespans. Most individuals are older when they die, but there are some people who die when they're younger. And so those are all examples of negative skew or a left skew. If the right side of the distribution extends further out, the distribution is skewed to the right or has a positive skew. The distribution has a long right tail. When you look at the graph, you will notice that most of the data values and the peak are on the left. The tail of the distribution is pointed toward the right, where there might be high data values that could be outliers or extreme scores that, again, don't really fit with the rest of the data. Examples of distributions that are right-skewed or have a positive skew include students' scores on a difficult exam. So here, students earned lower scores, and so their scores are piled on the left, and a few of the students might have higher scores, and that's pulling that tail to the right. Other examples include household income, where most people are earning lower wages, and then you've got your millionaires and billionaires that are pulling that tail to the right. Same thing with housing prices, where you have people who are buying houses. Most of them are paying relatively the same amount of money for their houses, and then you've got, of course, those houses that cost millions of dollars that are pulling that tail to the right. Next lecture, we will discuss measures of central tendencies.